So for this lecture, I'm going to talk a little bit about some features of the finite element solution of linear elasticity, what to look for, what some possible problems you might have, and yeah, which assumptions are needed to use the theory of linear elasticity and when is it going to break down. So the first thing, just as a reminder, the strong form of linear elasticity is this force balance, and then we have the weak form, and this is what we solve with the finite element mesh. I guess I've never used this before. Well, anyways, um, so the things that we introduced at some point in the verification of validation lecture is what is verification? Is the process of determining that a computational model accurately represents the underlying mathematical model and the solution. And in other words, are you actually solving the PDE that you say you're solving? And then what is validation? And that is the process of determining the degree to which the model is an accurate representation of the real world. In other words, whether your PDE actually represents reality. And that's the second point is the first one that I want to tackle here, which is when we say we are solving a linear elasticity problem where we want to analyze the stress at a part and we're using the linear elasticity assumption, what do we mean? So when is this going to work and actually represent the physical world? One aspect of it is we need small deformations, a maximum of around 1% strain. So if you have strains that are bigger than that, then it's more likely that you won't be able to describe the problem with linear elasticity. So at bigger and bigger strains, you start getting some nonlinear effects, both from the geometry and also probably the material properties. So make sure that your strains are small, and then you'll be fine. Then linear elasticity should describe the material. Another one is that the material has to be linear. That's why we call it linear elasticity. So a material has to be linear, and they have to be in their elastic region. And this is, for example, the classical engineering materials, steel, aluminum, and so on. Won't work for other materials that are very soft. So this won't work for rubbers, for example, because rubbers are non-linear materials. Then another one is that in the linear elasticity problem, we are not solving for the accelerations or velocities, so this is a static problem. Therefore, make sure that the inertia forces are at least an order of magnitude or less compared to the internal forces, compared to the stresses. And for that, what you need to do is to estimate the accelerations in order to know whether or not you're going to exceed the inertial forces are going to be significant or not. Um, Another one, and this is similar to the other point of the linear materials and staying within the elastic region of the material. Make sure that the material is going to stay within the elastic region. Therefore, that the yield point will not be reached. So the moment you go into that, then you start to have damage or plasticity. And what we have covered in class so far, it's not enough to represent that. And it's not that it cannot be done with finite elements. It can be done, and it can be done in Abacus actually. So Abacus has all these capabilities to do damage, to do plasticity, but to do nonlinear materials. But specifically, what we have done in this class has not covered that part. So you have to be careful with that. And finally, again, we are not doing anything about crack, nucleation, or propagation. Therefore, we have no fracture mechanics. So again, that's something that is doable within Abacus and with finite elements, but we're not doing it here. So if you are using this type of formulation that we have introduced and the examples that we have done in Abacus, they will work well for many instances, just not for any instance that you might be interested in. And therefore, what I suggest is that if you are interested in other elasticity problems, such as damage or plasticity or fracture, then you'll have to dig a little bit deeper into into the way to model these phenomena and probably take a few more classes. And so that's just something that you should keep in mind, because every more that you add to the physics of the problem, then you have to understand a little bit the physics and also the numerical analysis. What are a few characteristics of the solution for the linear elasticity problem? One of the characteristics is that these solutions are smooth, and this is because, and this is a technical term, this is an elliptic problem. There are other types of PDEs that have different features in their solutions. This type of PDE that we're solving, or the heat transfer problem as well, are problems that have just this second derivative. For the heat transfer, it was the second derivative of the temperature. Here, we have the divergence of the stress, but that is actually related to the second derivatives of the displacements. And we have no first order derivatives. And then we have some body force. So these type of problems that have just a second order derivative are elliptic problems, like diffusion or the elasticity problem, and they are nice. They have smooth solutions. And this is not the case, for example, for the wave equation or elastodynamics that we have not covered in class. And again, if you want to do a problem that has some wave propagation or some shock, something along those lines, then you would have to just be a little bit careful, and then again, just read a little bit more, try to look for what are the pitfalls of the numerical method for these other types of problems. Again, what we are doing works really, really well for these elliptic problems, what we have covered in class, but it won't generalize to all problems. Another thing that is a characteristic of our problem is that because it's an elliptic problem, and because we have just the second derivative, then the equations are symmetric. And actually, when you discretize with the method that we described, which is we use the same shape functions for both the solution and for the weighting functions, then you get a symmetric system of equations. And that's nice because symmetric matrices are easier to work with numerically. So for Python, for example, or MATLAB, it's a lot better to have symmetric equations. That's another feature. Then same Benan principle, which is that perturbations smooth out. So you don't have to have the perfect geometry or the perfect loading. You can have some approximations to the loading of the geometry. You might not capture absolutely all the details of your geometry or the perfect loading scenario, but in reality, even if you don't have that perfect, so you'll have some error, but as you move away, that error will decay. So one of the errors that you might have, for example, is that point forces lead to singularities. That is extremely large stresses. And you have probably seen that we did this at some point. For the beam bending example, we actually applied a shear force, but we applied it as 2-point loads. So we did a simplification there. We didn't really apply the force in the entire face of the cantilever beam, but that was fine because even though it was not the perfect loading, it overall produced the deformations that we expected. So again, you can do some approximations to the forces, and you will have some error, but it won't affect the entire solution. But you have to be careful. So in some cases, you should not be applying point forces because they lead to singularities, very high stresses that are not realistic. So in many cases, especially for example for quadratic elements, you might want to reconsider try to apply actual tractions, force per unit area instead of point forces. Another recommendation is, and we have talked about this, that for your project, for example, you might have a 3D part that you are interested in, and you might want to solve the stress analysis problem with the 3D geometry, but that takes a lot of time, especially if you want an accurate solution. We have done a little bit of mesh convergence analysis, and then as you refine the mesh, you get a better solution. And then in some cases, you need really fine meshes depending on the problem and depending on the geometry, and that just increases your computational power exponentially in 3 dimensions compared to 2 dimensions. And therefore, you have to be thinking about that and avoid the 3D problem, especially at the beginning. And this is related to what we have been doing in the project. What you want to do initially is you want to have a 2D approximation to the problem, to then find some characteristics of the solution, get a little bit of more intuition about what the system is doing. It's not going to be perfect, especially if your part is actually 3D, but it's going to give you some idea of the stress distribution, and then you can upgrade to 3D once you have done a little bit of simulations in the 2D case, the simplified case. What are the 2D approximations that you have? We have plane stress, which is for thin structures. Then we have plane strain, which is for thick structures, but there's no deformation across the thickness. And then there's axisymmetric problems, which is, for example, solids of revolution. And that one is a little bit trickier. We haven't really covered that in class. For the plane stress and plane strain, it's basically what we have done, works well. And as I've introduced in a couple of lectures before in linear elasticity, we have this D matrix, which has the material properties. And you can just change that for plane stress and plane strain. And the axisymmetric one, as I said, it requires a little bit more things to do. So yeah, just take it take my word for it that you can describe solids of revolution with an axisymmetric finite element formulation. Abacus has one. Yeah, so you would have to just look a little bit into it to be able to do it. I think I'm gonna stop. Yeah, well, no, I think this is the last slide, and then I'm gonna stop. The plane stress and plane strain, these are, for example, the D matrices, and that's all that changes. For the axisymmetric, actually, you do have some change in the formulation that we're